My name is Bill Sweeney. I am just about to finish my master's program in aviation safety. I was a pilot in the regional airlines for about 8 years, and I'm currently flying charter out of Kansas City. And my research topic is on the over-reliance on automation during flight training. Advancements in technology, particularly automation in flight decks, have made aviation an extremely safe mode of transportation. Traffic collision avoidance system has made near misses and mid-air collisions a rarity. Global positioning system and the use of the autopilot has made it so pilots do not often have to touch the flight controls, except maybe for takeoff and landing, although some aircraft have auto-land capabilities. Accidents are rare in commercial aviation, in part due to these technologies. However, there is concern among aviation authorities that many pilots that have gone through flight training recently lack the basic manual flying skills needed when the automation in the flight deck malfunctions. Some newer pilots struggle with shooting basic visual approaches, a very common type of approach to landing. The FAA has begun to change the training curriculum at the air carriers to ensure that pilots are trained on using the automation on their aircraft, along with maintaining proficiency in manual flight operations. Technology is evolving at an ever-accelerating rate. This technology has helped to make air travel the safest mode of transportation available. It does, however, take a lot of effort to keep up with the changes in technology, particularly when pilots fly multiple different types of aircraft, like in certain charter operations. In the midst of trying to master a particular avionics suite, fundamental manual flying skills are being passed over, and this oversight is a suspected culprit to a handful of recent accidents. This is a major concern by some authorities, such a major concern by some authorities that members of the House Transportation and Infrastructure Committee, along with the Subcommittee on Aviation, got involved and examined the FAA's oversight on the use of automation. This division wanted to make sure that pilots were being trained in the use of their automation and also how to manually fly the aircraft. It is estimated that automation is used during 90% of the time in flight. The FAA has established processes that oversee the training required to use and monitor automation in flight decks. There is little to no processes in place to ensure that pilots can also manually fly their aircraft or monitor the flight path and systems. This second aspect is referred to as pilot monitoring. Some air carriers do provide training on pilot monitoring. However, they are the minority. The major concern is the manual flying abilities of newer pilots and the training at the air carriers in manual flight. A safety alert was issued in 2013 by the FAA, encouraging carriers to promote manual flying skills in training and on the line. There's not been a determination whether or not air carriers have implemented these recommendations into their training. Further developments and guidance are continuing, and air carriers must comply by 2019. Flight deck design has become increasingly more streamlined and effective. The old steam gauges have been removed and replaced with LCD screens containing all the information needed to safely fly the aircraft in one location. Without a doubt, the automation has become extremely reliable and useful in the safe completion of a flight. Information is input into the system by the pilots and through the auto flight system, including the auto throttle system. A pilot can monitor the systems essentially the entire flight and not touch the controls at all. This has caused multiple concerning reports about the deterioration of basic stick and rudder skills, including a report in '96 and another in 2013 from the Flight Deck Automation Working Group. Vulnerabilities in pilots' manual flying skills, awareness of aircraft speed and altitude, and reliance on automation were the major issues. This is my first slide. It's the evolution of the Boeing 737 flight decks. To the left is mainly steam gauges, and as you look to the right, it's mainly the LCD screens of a more modern 737 flight deck. Recent accidents and incidents. Air France Flight 447 had departed Brazil, and 1 hour and 36 minutes into the flight, the aircraft was headed for a notorious area of bad thunderstorms. The very experienced captain had gone to the back, leaving the two lesser experienced pilots at the controls. As the Airbus 330 enters the perimeter of the storm, an electrical smell fills the cockpit and an unusual sound is heard, outside of the aircraft. Pitot tubes responsible for delivering airspeed data to the airspeed indicator ice up, ultimately disengaging the autopilot. Under great psychological stress, one of the pilots begins a steep climb, 7,000 feet per minute, and as the airspeed starts to bleed away. After multiple level offs and subsequent climbs, the pitot tube heat begins to do its job and clears away the ice, and the airspeed data is now accurate. Pilots are still not able to hand fly the aircraft and interpret the instrumentation data and could not determine why they had a nose up pitch attitude but were still descending. Even after the captain enters the flight deck and takes his seat behind the two co-pilots, they were still unable to correctly assess the situation and take control of the aircraft. This plane is in a stalled condition and eventually crashes into the sea, killing everyone on board. Asiana Flight 214 was on a visual approach into the San Francisco International Airport. The weather was clear, and there were 4 crew members in the cockpit, 3 captains and 1 first officer. One of the captains had been observed for his new role as check airman. The first officer was the pilot flying, and the data from the flight data coordinator indicated that the Boeing 777 was initially low on final approach. At some point, the first officer disengages the autopilot and hand flies the aircraft to correct for the flight path. The first officer eventually gets too high and sets the auto throttle speed to 137 knots for the final approach speed. Unbeknownst to him or the crew, the auto throttle system will fail to keep the selected speed due to the first officer's flight director being selected off. By selecting the flight director off, on only one flight director, the auto throttle fails to wake up and keep the selected approach speed. Because of the preoccupation of the glide path and the failure to adequately understand the autopilot auto throttle modes, the airspeed eventually bled off to the point where the stall protection system was engaged via the stick shaker, and eventually the Boeing 777 crashed just short of the runway and resulted in 3 fatalities. It's my second slide. It's a picture of Asiana Airlines Flight 214, the aftermath after the crash just short of the runway. Air India Express, operating a Boeing 737, was over the Arabian Sea at 37,000 feet with 2 crew members on board in the flight deck. The captain went to the back to use the restroom, leaving the first officer at the flight controls. The first officer had 1,000 hours of total time in the 737, more than enough time to handle most situations in this particular aircraft, according to investigators. The autopilot was disengaged at some point during this period and entered a steep descent, plunging 21,000 feet to 21,000 feet. The captain, sensing the unusually steep descent, rushed up towards the cockpit and entered the emergency code to get in. Upon opening the door, he noticed a 23-degree angle descent on the primary flight display, and the first officer attempting to manipulate the auto flight control panel in order to arrest the descent. The captain eventually took over the controls and manually flew the aircraft out of the unusual attitude. Colgan Air Flight 3407 was operating a flight into Buffalo, New York at night in light snow and fog conditions. The captain was flying and had 3,379 hours of total time and 111 hours in the Q400 in which they were flying. The crew was shooting the instrument landing system to runway 23 and had the anti-icing equipment turned on for some ice building up on the leading edge of the wing. The crew was using the autopilot, and the captain started to configure for landing by extending the landing gear and calling for the flaps to be set to 15 degrees. The airspeed bled away, as it does when the aircraft is configured for landing. However, power was not appropriately applied to maintain adequate airspeed. As the airspeed continued to decline, the stall protection system engaged the stick shaker. The captain pulled up on the flight controls, inducing a stall and sending the aircraft into an unrecoverable spin into the ground, killing all on board, plus 1 on the ground. FAA process of assessing manual flight skills. There is currently a lack of assessment by the FAA in determining a pilot's ability to monitor automation and hand fly the aircraft. There is no process in place to determine that an air carrier's training addresses the shortcoming either. Pilots need to be familiar with the autopilot modes and to be able to monitor the aircraft's flight path. There are recent incidents and accidents that are directly related to the failure to adequately monitor the automation. In 2013, a UPS aircraft crashed in Birmingham, Alabama after the crew failed to monitor the aircraft's altitude. Inspectors are trying to devise better ways to evaluate pilot monitoring skills. current process is through callouts. However, this method leaves much to be desired. Industry experts believe that they could develop training methods that incorporate subtle failures in the auto flight system that keeps the pilot engaged and constantly monitoring the aircraft systems. According to two particular studies, the CAST Airplane State Awareness Study and the Flight Path Monitoring Study, many accidents and incidents were directly related to the failure of correctly monitoring the aircraft systems. Detecting, challenging, and correcting pilot errors, while also the development of clearly defined monitoring tasks were the major recommendations from this study to improve pilot monitoring skills. Crew resource management has been taught as a valuable tool in maintaining situational awareness and does help in the overall monitoring of the aircraft systems. However, it does not completely resolve the issue of the shortcomings in pilot monitoring duties. According to the Flight Path Monitoring Study, CRM provides little guidance on how to manage attention when juggling concurrent task demands. The new FAA training standards do not ensure that monitoring skills are addressed during evaluations. Air carriers are not required to evaluate a pilot's monitoring skills during a proficiency or line check, and have said that it would be inappropriate for a standalone event. Pilots are evaluated on their ability to monitor the aircraft's operation, and air carriers are also required to incorporate pilot monitoring into their procedures along with their simulator training. Metrics are also lacking in evaluating pilots' monitoring skills. The NTSB has recommended that all training programs emphasize pilot monitoring until the FAA develops a standard training regimen. Common problems with automation. Since the 1960s, there was a requirement to limit the rate of climb or descent to 1,000 feet per minute or less for the last 1,000 feet of a level off. This was published in the Airman's Information Manual until about 1984. Around that time, there were an unusual amount of altitude deviations and major concerns over possible mid-air collisions. Around the same time, aircraft were beginning to be fitted with second-generation automation that used flight directors and autopilots capable of making smooth level-offs from climbs or descents of up to 4,000 feet per minute. This was accomplished by an internal logic that began the level-off without loading the aircraft beyond plus or minus 0.2 Gs. The altitude deviations continued, however, and one of the worst offenders was the MD-80. It was determined that the reason behind this was the crews were changing the vertical speed to 1,000 feet or less for the last 1,000 feet before their intended altitude, and the crew would unknowingly disrupt the altitude capture feature. The loss of the altitude capture mode would go unnoticed by the crew, and the aircraft would fly through the intended altitude. In some aircraft, as a pilot pushes or pulls the flight controls while the autopilot is engaged, the autopilot will trim the aircraft to counter the forces. China Airlines Flight 140, while on approach to Nagayo Kamaki Airport in Japan, encountered such a situation when the Airbus A300-600R stalled and crashed after it pitched up 52 degrees and stalled at 78 knots. According to the flight data recorder, the captain took over the controls of the aircraft from the first officer, and the aircraft was in the go-around mode with the autopilot engaged. The captain pushed against the flight controls in an effort to lower the nose. However, the autopilot trimmed the aircraft to counter the forces, leading to the inevitable stall of the Airbus. Had the flight crew disengaged the autopilot, it would have been easy to lower the angle of attack and recover. One of the more devastating autopilot malfunctions is the trim runaway, which is usually a memory action item for most aircraft because of the immediate need to remedy the malfunction in order to not overstress the aircraft or keep it from diving down into terrain. Unlike many other malfunctions, the trim runaway needs to be addressed within seconds and is part of the certification process of most aircraft. Present certification standards require that an autopilot system cannot place the aircraft in greater than 60-degree bank nor place undue loads on the airframe within a reasonable amount of time. This has ultimately been operationalized as within 3 seconds of the initial detection of an uncommanded bank, and applies to pitch and pitch trim test and ensures that the aircraft cannot stall, exceed speed limits, or require excessive control force during the recovery. Study on subtle and non-subtle automation malfunctions. Uncommanded roll and pitch trim malfunctions were the easiest to diagnose according to a study by the Civil Air Medical Institute in 1997. Commanded roll failure emulated an autopilot commanded roll that exceeded the target bank angle. Analyses for both roll malfunctions and the soft pitch malfunctions are based upon time from initial failure to disconnect the autopilot by any means, such as the yoke mounted disconnect button, panel disengage button, or circuit breaker. Times range from 1.8 seconds to 107.1, and 69% of the pilots disconnected within 13 seconds of the initial failure and half within 8 seconds. These immediate disconnects by 18 of the 29 pilots were defined by sequences where no other significant actions occurred between failure onset and autopilot disconnect. A response time of 8.7 seconds was used as a cutoff value. 93.7% of the sample of immediate responders were included. 10 of the pilots who chose to manually override the autopilot, 90% had chose times of 48.3 seconds or less. Scores were log transformed for analyses to remove the skewness found in response time data. The log transformed disconnect times for the two groups with the highest and lowest extreme times were removed indicated a significant difference between the immediate disconnects and the manual overrides. Another subtle failure is called a soft roll failure of the autopilot, and according to studies is more difficult to diagnose than a trim runaway. It is typically easier to correct for once diagnosed. According to the study by Behringer, pilot performance was categorized in either immediate disconnect or manual override. Those categories categorized as immediate disconnect responses averaged 11.72 seconds, ranged 13.6 to 85.14, while those categorized as manual overrides averaged 37.45 seconds, ranged from 13.6 to 85.14. 88% of all immediate disconnects occurred in less than 14 seconds. Post hoc comparison indicated the mean difference to be significant for both raw and log transformed score. Log score is F statistic 1 and 26 equals 27.07. Soft pitch failure of the autopilot pitch sensor was also examined in the study. It was rated the most difficult to diagnose and was rated third easiest to correct. The performances were categorized by immediate disconnect and manual override. 3 of the pilots in the study did not diagnose the failure. Manual flying the aircraft without disconnecting the autopilot. The author removed them along with another outlier, leaving 13. Immediate disconnects averaged 17.7 seconds, ranged 6.5 to 31.5, and manual overrides averaged 46.19, ranged 15.2 to 76.2. Approximately 50% of the immediate disconnects occurred in less than 16 seconds, with 85% occurring in less than 24 seconds. Post hoc comparison of the log transform data showed the distributions of the two types of responses to be significantly different. Runaway pitch trim was the last failure to be analyzed and was different from the other failures, in that only by pulling the pitch trim circuit breaker would the problem be corrected. In the interim, the pilot could press the autopilot disconnect trim interrupt switch. Only 3 pilots chose the optimal response, was to press the disconnect trim interrupt switch, then to pull the circuit breaker. 4 others depressed and held the disconnect at various times during the recovery. Most of the volunteers initially pressed the disconnect button on the yoke to disengage the autopilot, followed by the panel-mounted disconnect button, mode manipulation, manual override, and pitch trim circuit breaker. 21 of the 25 pilots considered were classified as immediate responders. 2 were classified as manual overriders and 2 as mode changers. The author was interested in 2 particular times. First, the time required to detect a malfunction and initiate some action, either autopilot disconnect, control wheel steering, autopilot engage, or circuit breaker. And second, the time lag between the initial action and the pulling of the pitch trim circuit breaker. Average time for the 25 pilots was 10.46 seconds, with all except 1 response over 3 seconds. 50% of the responses occurred in less than 7 seconds, with 65% of the cases in less than 9 seconds. Time to pull a pitch trim circuit breaker averaged 35.4 seconds, with an average lag of 22.69 seconds between the initial response to the runaway pitch trim and the required remedy. The volunteers of the study were briefed on how they were able to manually overpower the autopilot servos, and 22 were aware of the potential interactions between a runaway pitch trim motor and autopilot pitch attitude inputs. Volunteers were asked about their recovery strategy for dealing with an autopilot malfunction, and the group voiced two strategies along with the third strategy, which was a combination of the two. The immediate disconnect strategy was endorsed by 9 individuals, and 2 others had a similar strategy, so that they were lumped in with this group. 5 of the volunteers said that they would fly the aircraft through the malfunction while they tried to diagnose the situation. The third group stated that the strategy was malfunction dependent. These 7 participants stated that they would most likely fly through mild failures, disconnect for severe failures, or diagnose while using an autopilot, then disconnect. This last group, using the fly-through approach, would be referred to as using a manual override strategy in the study. The author of the study was interested in response times in different modes of flight. During certification, the delay is to be 1 second during a coupled approach, and the experimental procedure was set up to examine the pitch trim failure during cruise climb and the coupled ILS approach. The aircraft is more likely to have a slow airspeed in these conditions than when the failure is detected in level cruise flight. Independent samples t-test indicated no significant mean differences between the response times for these 2 flight modes. A significant difference for the circuit breaker lag was found using the Levine's test of variability, with the F statistic equal to 3.406. The group that experienced the failure on climb out was more variable in their responses than was the group receiving it on the approach. It was determined that no significant effects of mean or variance difference were found. The first analyses could support the assumption that pilots were more attentive on approach. However, the log transform scores would tend to downplay this explanation. Comparable analyses of all the other reaction time variables, either command roll, soft pitch sensor, soft roll sensor, were used to determine if the differences might represent an inherent difference between post hoc groups, either climb or approach. The significant mean or variance differences were found for either the raw transform score, suggesting that the 2 groups of pilots were not significantly different in their performance on the experimental tasks. The relationship between the stated strategy, flight experience, and response time were examined using a point biserial correlation method. There was no systematic relationship found between the number of flight hours and the strategy used in the simulator. The relationship between reaction time and the selected strategy was significant, since those pilots who chose to manually override the autopilot had longer reaction time values. Values range from 0.69 to 0.47. There were also a significant correlation between occupation and roll sensor failures reaction time, most likely due to 4 out of 5 FAA pilots adopting a manual override strategy for this failure and had longer reaction times. Using the Pearson correlation method, correlations were calculated using reaction times to time since last experienced autopilot failure, with significant P greater than 0.05 values for soft pitch failure and R equal to 0.48. Runaway trim, R equals to 0.54, and commanded roll, R equal to 0.38. Pilots who recently experienced an autopilot malfunction were more likely to respond quickly than those who had not. There were also significant correlations between roll sensor reaction times and 3 training experience measures. Dual instruction received in the last 24 months, with R equals 0.73. Simulated instrument time during the last 12 months, R equals 0.66. And the number of hours of simulated instrument time in the last 3 months, R equals 0.62. Certification practices assume that when a malfunction occurs, it will be severe enough that certain cues, whether from an alerting system or the production of super-threshold cues, begin in the 3-second recognition period. Autopilot prototypes are often rejected when the 3-second period is broken during the testing phase. During the study, the pilots required an average of 5.9 seconds to identify the malfunction. Some required 11.8 seconds. The malfunctions in the first part of the study were more subtle, and the pilots who chose to fly through the malfunctions, then diagnosis, did not place the aircraft into an unrecoverable attitude. The recommendations from this part of the study was to increase the waiting period for command over and sensor loss failures to accommodate at least 75% of the pilot population. Consider eliminating separate treatment of approach and other flight modes, giving no detectable pilot response differences. Pursue additional failure enunciation or fail-safe modes from manufacturers, and to continue use of attitude and performance limitations as ultimate criteria for acceptance. The second part of the study was to explore the more hazardous and more subtle malfunctions. The design was a single factor within subject design using autopilot malfunction type as the independent variable. The malfunctions were from largely covert to largely overt, i.e. running roll server, roll rate equals 12 to 15 degrees a second, which is overt, and attitude indicator, ADI failure, slow drift, autopilot tries to follow failed instrument, covert soft pitch failure, rate equals 0.2 degrees a second, which is covert, and runaway pitch trimmed down, initially covert, then becoming overt. Dependent variables including flight performance data and states of critical controls, autopilot disconnect, engage, circuit breakers, and pitch trim switches. The second part of the study concluded with 13 of the 24 participants encountering flight terminating circumstances, with neither the mode of flight nor the auditory alarm affecting the outcome. Important recent studies on manual flight. A 2010 study on a pilot's ability to manually fly the aircraft when the automation malfunction was called the Flight Safety Foundation Study. The study used a 5-point scale where a score of 4 was needed to meet the FAA standards. Their finding was that pilots had average scores of 3.2 for the takeoff portion and a 2.4 for the load during hand flying and during holding patterns, both of which are below FAA standards. They attributed it to the declining of the pilot's manual flying skills and the overestimation of their manual flying proficiency. These also concluded that pilots' basic instrument skills can decline over time. The recommendation was to ensure that pilots are competent when automation is functioning, and also when there is a malfunction in the auto-flight system and/or instrumentation. NASA conducted a study in 2013 where pilots were presented with abnormal events under predictable circumstances that were scripted, and abnormal events that were less predictable, more like events that a pilot would encounter on the line. The findings were that the responses to abnormal events they encountered during airline training may not generalize well to real flight settings. The recommendation from this particular study was that pilots should turn off the automation during training in order to better learn how to identify abnormal situations without any alerts from the aircraft alert system or its automation assistant. Flight Deck Automation Working Group did a study in 2013 that identified vulnerabilities in pilot knowledge and skills that led to increased errors during the manual flying of aircraft. The study's authors recommended that the FAA should develop standards to maintain and improve knowledge and skills for manual flight, to include opportunities for pilots to refine knowledge and practice skills during training and checking of flight path management policies on the type of aircraft. Another study by NASA this time in 2014 found that pilots struggled to maintain the cognitive skills that come with manually flying the aircraft, such as awareness of the aircraft's position and recognizing instrument system failures. They concluded that pilots should be offered additional practice in manual flight, and the study also promoted the use of more active automation monitoring practices. These particular studies found that pilots should have opportunities during training to practice and hone their manual flying skills. Over-reliance on automation has a degrading effect on the skills needed to hand fly the aircraft. The FAA also found that automation was used 90% of the time during the average flight. Pilots also tend to overestimate their manual flying skills as well. A study by the Flight Safety Foundation in 2010 evaluated the manual flying skills of 30 experienced U.S. airline pilots and found that scores for manual flying maneuvers were well below the FAA standards, even though the majority of the volunteers claimed that they hand flew the aircraft below 10,000 feet. These applicants were not able to fly the aircraft manually using basic instrumentation when a failure in the auto-flight system occurred. in response to an alert by the Pilot Training Rulemaking Committee in the Flight Deck Automation Working Group about the deterioration of hand flying skills. The FAA issued an alert to airlines about the need to promote manual flying skills. The concern was that pilots rely on automation too much, and the fear that airline pilots would not be able to deal with unpredictable and non-routine issues such as a failure of the auto flight system or instrumentation. Many airlines discourage their pilots from hand flying. In fact, especially during departures and arrivals into busy airports, pilots often are told by their employers that the aircraft should be flown with the highest level of automation, and hand flying should be used only in low-threat environments. The FAA has again yet to provide basic guidance on evaluating pilots and their manual flying skills, despite industry experts warning that airlines need to increase the opportunities and training for manual flight. The opportunities of hand flying are a rarity in modern aircraft and airline operations, and airlines have not adjusted their training programs to compensate for this program. A study after study conducted to address this issue, the FAA has yet to offer guidance to air carriers. NASA has conducted a study offering recommendations as well, concluding that airlines should encourage hand flying during normal operations and include manual flying maneuvers during recurrent training. There is little to no tracking of the training exercise performed manually compared to the ones performed using automation, as well as the actual time spent on manual flight training exercises. The FAA has established some training requirements to address manual flying skills during takeoff, landings, and abnormal events, such as single-engine ILS approaches, which are often flown using raw data and without the autopilots. Much of these requirements allow for the use of some automation during training. Many pilots, because of the fear of busting a check ride or proficiency check, will turn the autopilot on as soon as they are able to. The increased training requirements by the FAA includes manual flying out of an unusual attitude, an arrival and departure procedure, conducting slow flight, and losing a reliable airspeed indication. This will hopefully help trainees to understand the performance of the aircraft and the way it handles at airspeeds just above the stall warning. The recognition and appropriate response to the malfunction of the pitot-static system, and to be able to recognize when the aircraft is in an unusual attitude and use basic instrumentation to level the wings and reduce or add appropriate power to recover. There's also been training added to demonstrate the proper way to recover from a stall stick pusher activation, especially at high altitudes, and also recover from a bounced landing. Mandatory compliance is not required until 2019, however, so some operations still lack the needed training. Conclusion: ensuring that the national airspace system remains as safe as possible for the traveling public is a huge undertaking for any organization or organizations. There are many different parts of the puzzle, one of which is the actual pilots maneuvering the aircraft within these boundaries. It is extremely important that these pilots are very competent and professional, and that without a doubt that they're able to manually take over the controls of the aircraft that they are trained in and hand fly it should there be a failure in the auto-flight system. This issue was relatively non-existent not too long ago, when the flight crews would manually fly the aircraft for every single leg using only basic instrumentation in the process. With the seemingly exponential increase in the technology of modern auto-flight system, there is a major fear among industry safety experts in the failure of pilots to maintain these fundamental basic stick and rudder skills should there be a failure of some sort. Training requirements and evaluations need to be introduced to every air carrier operation, and hand flying encouraged instead of discouraged because of fear of disrupting operations around airports, particularly busy airports. The FAA should improve its guidance to inspectors for evaluating air carriers' policies and training programs in this area of manual flight, helping to ensure that professional pilots are competent in using their particular auto-flight system and also able to take control manually should it fail. All right, thank you.